Hello, everyone. My name is Jamie O'Rourke, and we're going to be talking about cloud computing. I chose cloud computing because it's relevant enough in modern times, and it seems to be only growing. Also, I could have picked a specific subtopic of cloud computing, like say maybe a company AWS that offers every category of cloud computing services. However, I feel like there's enough arbitrary categories in cloud computing. It's kind of been generalized almost enough to where it can get a little mysterious behind the idea of the cloud. So, without further ado, let's go ahead and jump on in. All right. So, go ahead and jump over to the topics covered. So we'll be talking about before the cloud, where the cloud itself came from, services offered. That's going to be a really important one. And deployment models, which is different types of clouds. And of course, the security and privacy, the risks and threats involved, whatnot. And then also we'll touch on where we are now and leaning into the future with multi-cloud and edge computing. Also, another one called multi-access edge computing, which is just another enhancement of edge computing, and we'll discuss that. All right. So before cloud computing, we'll rewind back all the way to the 1940s, and we have serial processing. We can send instructions, which compared to not being able to send instructions, that's pretty good. So that's saying something. Then we have parallel, where you kind of we'll go over pictures of each of these so we can kind of see what's happening generally. And then after parallel in the 50s, we get to the 60s, where we can do things with the parallel sets, and we can distribute them in certain ways, starting in mainframes and chipsets and whatnot. And then after a decade or so of kind of playing around with that, we can apply it to networks of devices, each containing their own processing power. So by the early 70s, we had LANs, local area networks of multiple devices with the ability to work together to accomplish a like goal. And then a decade or two of that distributed processing, we see grid. And grid is really the same idea as distributed. It's just upscaled and generalized to kind of be more of a one-size-fits-all and can cover more ground. So looking at serial on the left and parallel on the right, this example is, say you have n number of employees. Each employee will have to wait for the employee before them to get completely done with every single aspect of the payroll function. So employee 1 has to go all the way through the payroll function, and then employee number 2. And then we get this, right? And then parallel is you get to line up the multiple serial lines, and now employees don't have to wait. Each employee can execute their own payroll function simultaneously. So that's the idea between serial and parallel. And then distributed, now I am missing a little picture here that would really, in a good way, help describe how distributed can also work on a chipset. Distributed also works within the devices as well. But what I have right here is distributed being applied on a network level. So this is a local area network, and grid it can kind of see a similarity here. So we're not really looking at the individual end nodes. We're not really looking at the end devices so much anymore. Now we can say, hey, we have this giant local, this giant, all these giant networks that can work together and create a bigger network that can really accomplish with all these devices that are all focused on helping this person. This person can really kind of accomplish whatever they want without having to worry too much about their own device or processing power. So, where the cloud came from. We kind of just seen it right there, right? So the grid, there's the grid of this network of networks, right? So way back in the day, before the internet, while this was all coming up in the 70s, there was the ARPANET, which is I can't remember the name verbatim. Forgive me. It was a American government funded program, generally for research, but also surely military purposes were involved there. However, within the ARPANET, there was a project, and that was the internet. So the ARPANET was this, they're figuring out data communications and whatnot, and then they realized that you can create a network, right, the LAN, right, the distributed system, but then when you just link it to another network, you can double the processing capability. You can increase the processing capabilities. In basically internetworking is that. So if you're working within one network, that would be intra networking, and if you're working within across multiple networks, it's inter networking. So that idea, the base idea of cloud computing is that right there. It's using a network of networks of processing that can be so seamless that you wouldn't even think there are servers involved. The network itself can work so well that it's seemingly a serverless processing method, even though there's servers involved. The idea is multiple nodes relaying data to and from sources and destinations, right? So, and that's really the idea of the internet. And we're about to see another picture of this too. So the idea is that your computer, right? Let's break it down to the basics. Your computer could just talk to another computer in some way, shape, or form. Without that, it's very simple. If your computer did not have the ability, if computers did not have the ability to communicate, to send some kind of senseful meaning to each other, well, then we don't have any of this. This is the very simplest Lego piece that we need to build on. We need this data communication. And as soon as we started that from computer to computer and then from network to network, especially, then we were already creating the cloud before we would call it the cloud. In fact, when the network was being created, the idea was generally the cloud without it being called the cloud. So, of course, in reality now, it's not as simple as computer to computer. Your computer has to talk to the modem, goes to the modem pool, goes to the internet service provider, goes to their routers, goes to their backbone, goes to the proper direction routing techniques to make sure that your computer actually gets to that other computer. And what does that look like on a big scale of a bunch of computers trying to talk to a bunch of other computers all at the same time? We end up with something like this over here on the right. Of course, way more complex than this, but even this is starting to... We're not getting so trivial anymore when you start to think about the different logical routes that could be taken here to accomplish whatever purpose is trying to be accomplished. So this right here is kind of that grid networking that we've seen. So that grid networking being applied on this massive scale, that is the internet. And as we'll see, this is, let's say you have some storage down here that you need to use, and over here you got this processing, these servers that can virtualize a bunch of operating systems and run this app on them to see how your performance. Let's say you built an app and you want to know how the performance is with multiple clients, when multiple clients are trying to run on one server, and you want to test that out. Well, you might need to use the processing power from over here. You might need to use the data from over here. These all need to be talking to each other, all while also talking, say you're over here. This all needs to be happening in a very smooth, nearly real-time fashion if it's going to replace localized processing. So the services, we're going to, I'm sure you have all seen the picture that I'm going to show next before, but we're all going to go, sorry about that, let's go back. All right, but we're all going to look at that and see the stack of what users are and are not allowed. But we see that there's the three main different services. Now I underlined main because these, let's not set these in stone. Let's look at these as like a speed limit sign on a highway. They are categories. They generally do describe the apps or service that they are providing, but like software as a service, there's a bunch of softwares. That's probably the most self-explanatory one. It's an app. Any app that you can use without putting any functionality on your device, without downloading any apps, while just using the app over a browser, then you are using software as a service. Now, there's a lot of ambiguity here because you could say, especially nowadays, software itself is becoming powerful enough to where you can blur the lines between, say, a platform, a function, and a software. So you can kind of say, where does let's say, there are others, and yes, there are other services other than these three. These are just the most popular. There's a function as a service, FaaS, and bunches of others. But that would lie somewhere in between, not quite platform, little less than platform, but a little more than software. There's other examples too that lie in between platform and infrastructure. So these are really just kind of blanket terms that they should not be set in stone. They shouldn't be held true to, well, what is this? It doesn't really seem like platform as a service or infrastructure as a service. Well, it probably is some combination of both in practice, in reality. So, also, the services keyword here. Oh, this is the table that we're all going to see. But let me go back really quick. The service is keyword here because since all of these networks of devices are all working together so seamlessly and so smooth that you aren't really renting a space on one server, or also like you aren't really renting one set memory stack from a server hall. You are using these resources that ultimately are geared in a way to forget about whatever you just told it whenever you're done, so that it's really just providing you what you want when you want it, which is much like I'm going to pay for my electricity. I flip the light switch on, the electric company starts billing. They start metering, they start watching. When I turn it off, they say, okay, great, we don't need to send you that anymore. We're going to start sending it to someone else. They're not going to say, hey, we reserved this energy, this battery just for you. This portion of the dam that holds the energy for, or however they store their energy, is reserved just for you. No, it's more like I am buying the service that they are providing. Now that, since we can have this seemingly serverless method of supplying processing power, we can kind of have it billed as a pay-as-you-go, much like an electric bill. We will just measure the amount of bandwidth and flow that you use and charge you accordingly, instead of having you rent out any pieces of hardware or anything like that. So that's a very important thing here with cloud, because it should be full circle almost by now that the cloud is really just the internet, right? The cloud is just taking advantage of the internet. So here's the different stacks of those really arbitrary but very popular three categories: the infrastructure, platform, and software. So with the software, you see the application, right? You just get the app. You don't touch anything in there. If you get behind the junk of that app and you can change something, Google would let's say you got into Google Docs and was able to change the home tab to Gnome tab, right? That'd be a lot of people who saw Gnome tab. That would be an enormous amount of people, and so that they would really appreciate it if the software, those who are using their software as a service, were not able to. Sorry about that. We're not able to use the functionality or manipulate the functionality or data of the application. And so, platform as a service. Excuse me. This is the least common of all of them, and it is almost always used for development purposes. So this only getting the application and data, but not really getting the runtime, middleware, or operating system, that's a really abstract idea, because an operating system needs to be there, right? It's not like the operating system disappears. It still has to be in this fine layer, right, of inaccessibility while providing performance. So you're still getting like a layer of operating system, just stripped of all rights and privileges, and it's in an environment structured for you to be able to build an application and manipulate some data, while not getting deterred, right? Not getting distracted, right? So it's almost like these three, the operating system, runtime, middleware, not being available, is beneficial for the development companies. It's not like something that's being restricted so the development companies can't be able to take advantage of these three. It's really more beneficial to remove these three, because we just want to do some testing and processing. We want to see how fast is my program. Can I make it any faster? I don't want to worry about any operating system garbage in the background. So the more you could remove of that for me, that'd be so great. So I can really see what does my code do. So that's the kind of tricky platform. I don't know why this is a main category, to be honest, because it's kind of a left turn, if you ask me. Really, the two main kickers are infrastructure as a service and software as a service. Mainly software as a service, but infrastructure as a service too. Notice they got the virtualization down here. At first, this was a confusing one, but I appreciate it, because you can, let's say you wanted to rent an infrastructure for a couple months from some company, let's say Google Compute Engine, and you wanted to have some apps, and because there's also Google App Engine, and you wanted to have some fun on there. Well, just know that there's that seemingly serverless processing. That's because you're not renting an actual space. Sorry about that. There's the examples again. They are virtualizing all of it. So you are in a server that is a virtual server that is inside of maybe another virtual server that is inside ultimately some physical server for the time being. You might get shifted over to another part of that server. You might get shifted over to a completely other server, depending on what that company needs to do with whatever they got. So just know this virtualization layer right here just means if you're going to rent this operating system, you can do virtualization again. You can make an operating system that makes operating systems, right? And you can split it into a bunch of virtual machines, and maybe you want to try to start your own company, and that's how you want to get a feel for it. So, with the examples of different types, just notice that, taking a look at these up top are going to be the most popular. They're going to be the most recognizable. Software is the biggest. As users, we just need to use what we need to use when we need to use it, and when we're done, that's it. So that is an application. That's a program. That is software. So if there's not much of a need to dive deeper, then we don't. So platform as a service, we could see probably the most recognizable out of here would be Azure. Unless you use Red Hat, you would know OpenShift. Google has Google App Engine. And then infrastructure, same deal. You'll notice like Google has all three. Amazon has all three. I don't think I included an Amazon one up here. Amazon.com. Amazon itself, right? What they started with would be up here. So a lot of companies can range in between. And like Google has way more than three, too. They got some some people would consider platform, some people would consider infrastructure, some people would consider like, this one has doesn't have the full operating system capabilities, but why can you diddle daddle with some middleware and runtime stuff, right? So there's a bunch more than here, but this is just a general layout. All right, now we have the deployment models. So really just think companies, because without a company or like an enterprise with money in mind or some kind of capitalistic goal in mind, everything would just be public and shared, and we would all trust each other, and there wouldn't be any malicious behaviors, right? In a utopia type world. But that is not the reality. The reality is that there's certain structures that are allowed for public. A company can come buy up a bunch of towers and communication lines, and they can create their own private cloud where they own that entire network. And so any public networking would have to go around them, even if it would be very convenient for the public networking to go through them. They would have to go around. So that gives rise to public and private cloud. And then there's hybrid cloud, where let's say for the most part whoever your company is, they got it down almost amazingly to where they can be a fully private cloud. But maybe there's some situations where they need to use that public line. Well, as soon as they use that public line, that data is visible. Therefore, it's a hybrid cloud. It's a different thing, and you wouldn't just want to still call it a private cloud if they're using anything public at all. And the last one is community cloud. So this is where a bunch of companies with usually all one common goal in mind get together, and it's kind of like a private cloud, like a multi-owned private cloud, I would say. So security, there's IP addressing, third-party security vendors, encryption and decryption. The only thing that's different about the cloud versus the internet that really stood out to me is the third-party security vendors. Other than that, it's subject to any IPv4, IPv6 addressing flaws. They're going to be present in cloud computing, as well as encryption, decryption. We're about to go over an example of AWS, but there's vulnerabilities for sure. So here's an example of that AWS. This is a use case medical record deployment for just random example. SNS means simple notification system. It's a AWS system for relaying information. So they go through HTTPS and they use envelope encryption. So they don't look inside the message. They receive the block of data. They encapsulate that block of data. Then they encrypt that encapsulation. Then they send it along. So they're not peaking. Great for privacy. Also, as soon as they get found out, someone can get to that envelope. So maybe the data inside that envelope was already encrypted, which would be great. If not, and AWS gets found out on their encryption, then someone could access it. If someone can access via IP addressing and decryption methods, then they got your medical record. So that it's not, the cloud is not some magically secure place. Definitely not. Also, privacy. There is potential for loss of data. It is centralized data, right? So you're next to your neighbors. Privacy breaches are going to occur, whether maybe on accident. Because the data and memory is all being handled by someone else, someone who doesn't know you on a personal level, or the person's data who's right next to yours. So mistakes can happen, malicious behavior can happen. So here's an example of what it would look like to have your data somewhere. So you're not only, you could see it, it's private data, you could see it. Not only you though. Your service administrator could see it, and not only them. If there is some kind of security purposes, which usually some company will have one, if not more, third-party vendor for security, they can see it too. So the privacy is it's at risk. And amongst those other, of course, there's the distributed denial of service, the DDoS, service hijacking. Give me $1 million and then I will return your resources. Malware infections, insider threats. This could be admin, your neighbors, right? An example of downtime is the financial losses. An example is the AWS Simple Storage Service, or S3. It went down for maybe 2.5 hours, something like that, and on February 28, 2017, they lost upwards of $150 million and affected millions clients, not even if not directly, then indirectly, because people were relying on the services that their clients provided, which no longer were provided when their storage service went down. So and this is just showing that as soon as the connection went out, down here, the packet loss went up, and there was no way, they had no plan in effect, contingency plan in effect to save anyone's memory. It was a full packet loss scenario, millions of dollars within hours, hundreds of millions within hours, over 100 at least. Also, there's multi-cloud. So this is just that same idea. We'll see. It's the idea is to distribute workloads, applications, and data. And say you have a private cloud and you're using or you're not using anything, you're just using the private cloud. But let's say through the internet, your private cloud needs to hop over on AWS's cloud, which is public. Well, your private cloud now is hybrid cloud because of what it has to go through to get the results that it wants. Now, the next thing is edge computing. So now we're kind of creeping into what's next for cloud computing. It is decentralized, the main idea. We're decentralizing the data and the processing power and data manipulation from the cloud. We're also decentralizing it from the local machines. So the node devices are going to help with functionality. So think routers. Right, so your router it's really great at directing traffic, but what if it could use a little something else too? What if it had an extension from the service that it's receiving to say, by the way, if that device you're talking to wants to send something up to the cloud, and if it's A through E, if it's any of these 5 things, well, go ahead and perform the functionality yourself. Here's the functions you would need to do that. So let's just say your router could receive processing ability from the data center. So it's not just sending communication anymore. So let's say that that happened with 2 routers before they reach the data center. There could be a lot of scenarios where the processing power never even reaches the data center. So let's take a peek. So we have this cloud right here, and then we have the edge nodes. We can think of the edge nodes, and these would normally be routers. These would just be relaying data, going here to here to here to here to here to here. And either, in today's reality, either this device here is doing processing work, or this data center, hyper upscale data center, is doing the processing power. Now we're starting to see, well, hey, well, that's a lot of processing, and then to be sent, however many miles, maybe hundreds of miles, maybe thousands of miles, to go be processed, and then being sent thousands of miles back. And sure, this stuff it runs really fast, but it could be thinking along the way. That the data could be, churned out. It could be, we could have gears kind of crunching out the data as it's sending it too. It's very abstract, very plausible though. It's receiving the data, and then it's deciding where the data should go. Is it possible to include a little bit of functionality there? I'm sure. Now, encryption and decryption in reality and practice are going to be an issue there, but that's part of the beauty of progression. So now multi-access edge computing, it's just a subset of edge computing. Now it's really focused on wireless, mobile, right? So whenever you hear multi-access edge computing, you're almost always going to hear mobile access edge computing. It's so really, it's applying that same concept to real life, to AI models, to machine learning models that need to be able to not be wired in, first off, and to be able to think in real time. So it needs to be able to almost work as a human, as if a human was operating it, without really needing much of the human. And a huge aspect, or a huge area where this is being applied, surely not too much of a shocker, is Internet of Things and industrial Internet of Things. So we could see the Internet of Things would be over here, the smart things, and it doesn't have to be IoT, but the communication is being sent to the 5G towers, right? The radio towers, right? And this is a great example to show you where bugs can exist and malicious attacks can exist too, right? So it does increase the vulnerability, right? Someone would have to actually get to your device and affect your device on a physical level if all the data and processing was held on that device. That is not the case. It is actually this super accessible, very easily accessible, massive network that it goes through. So it's going to be ridden with bugs every step of the way. And that's just the reality of the situation that we live in. So yeah, this is seemingly the future where there's this little multi-access edge computing area in between that traditional cloud internet and us as the end users, to where it's not just sending the data, it's crunching some of it too, and performing some functionality, reducing latency, including and increasing speed. So, conclusion: cloud computing is the next natural evolutionary step in computing. It is important to remember that these risks and threats, they've been around. It's not, computing brings very few new threats. If anything else, the threat, it will have a new name, and if you start to look at it and hash it out, it's an actual repeat of a threat that has been adapted to fit the game, if you will. So the future lies in the decentralization of processing. So whether it's decentralizing it from the cloud center or from the local device, it's kind of meshing everything together. All right, so that's all I had for you. Any questions for me?